In this video, we're going to look at the topic of differentiability and its relationship with continuity. A function f is what we call differentiable if the derivative from the left and right exist and are equal. So again, a function f is differentiable if the derivative, think slope, from the left and right exist. That means not infinity or negative infinity. And if those two values, those numbers, are equal. Right? Differentiability fails in one of three situations. When a graph is not continuous, two, when a graph has a sharp turn, and the third time the differentiability fails is when a graph has a vertical tangent. So for each of these three cases, let's look at some graphs. When is a graph not differentiable? Well, when a graph is not continuous. We're going to look at two different graphs. This graph is familiar to us. We can think of this as the absolute value of x over x, or x over the absolute value of x. Well, this graph is not continuous, so then this function is not differentiable. Now, it's differentiable on parts of the graph, but not the entire graph. We can respond to a couple of questions in two different ways. We can say that this graph f is not differentiable, I'm going to abbreviate, at x equals 0. So if we're asked to describe where is the graph not differentiable, we want to give the specific x values. Right? What if the question is, consider this graph. Where is this graph differentiable? Well, it's just the opposite of everything we said here. F is differentiable on, and we'll do interval notation, all real numbers except for 0. All right, let's look at a second graph that's not continuous. I'm just going to draw a random graph that has a point discontinuity. So this graph is not continuous, but it is continuous on parts of its graph. This graph is not differentiable, but it is differentiable on pieces or parts of the graph. So let me just label this as, I think, 2. So we can say f is not differentiable at x equals 2. But read the directions carefully. What if they ask you on what intervals is the graph differentiable? Then you'd say f is differentiable on all real numbers except for 2. So differentiability fails when we have a graph that's not continuous, and we can look at specific x values at which that fails. All right, the second situation when a graph is said to not be differentiable is when the graph has a sharp turn. So let's look at a couple of examples. I think one of the examples that we can use is the absolute value graph. So think about the absolute value graph. Okay, it has a sharp turn. If I'm not doing any translations and I'm just looking at the parent function, we have a sharp turn here. So the slope, and we want to consider what's happening at that sharp turn, which is at x equals 0. Notice the slope from the left is a negative number, but immediately at that sharp turn, okay, the graph has after that sharp turn, after x equals 0, we have a positive slope. So the slope from the left and the slope from the right exist. Maybe this is -1 and maybe this is +1, but those aren't equal. So two ways we can respond to a couple of questions is f is not differentiable at x equals 0. However, the graph of f is differentiable on every x value except for 0. So for example, if we were looking at differentiability, say at x equals -2, well, the slope from the left and the slope from the right of x equals 2 is the same. It would both be maybe -1, some negative slope. All right, let's look at another graph that might have a sharp turn. I'm just labeling them all f of x. Okay, let's say that we had a piecewise function and maybe perhaps the graph starts out maybe parabolic, but perhaps right here at x equals 4, the graph decides to become linear. It's continuous, but we have that sharp turn right there at x equals 4. The slope from the left is some positive number, and then all of a sudden it's some negative number here. So f is said to be not differentiable at x equals 4, etc. Now, just to be clear, we don't have to go from a negative slope to a positive or vice versa. We could have a positive slope, and what if all of a sudden I wanted to become linear, but instead of having a negative slope, I drew my second piece something like this? I still have a slope from the left that's positive, but immediately right here, the slope changes to another positive value, but not the same. It's not equal to what the slope was to the left of x equals 4. All right, so what's the third case when differentiability fails? And that's when a graph has a vertical tangent. Let's look at a couple of graphs that might have a vertical tangent. Let's say we have this cubic graph, and all of a sudden, it just becomes very, very steep right here. And then it goes on its merry way. So I'll call this x value 1. Okay, notice that right here at what we call a point of inflection, we'll learn that a little bit later. If I were to draw in a tangent line right here at x equals 1, my tangent line would be vertical. Well, what kind of slope does a vertical line have? It doesn't, no slope. So this graph is differentiable everywhere except for at the x value of 1 where we have a vertical tangent. Okay, let's look at another familiar graph that does have a vertical tangent as well. Just think of the square root of x graph. The square root of x graph, that parent function starts at the origin 0, 0, and even though we can't really see it very well, what happens is that graph leaves this point so steep, and then all of a sudden it has slow growth. So right here at x equals 0, we have a vertical tangent. We have a tangent line at that one point that's vertical. Well, what kind of slope does a vertical line have? No slope or undefined. So for this graph, f is not differentiable at x equals 0. However, it is differentiable on all other points of its domain. So for this graph, I would just do 0 to infinity, since I don't have any part of the graph of the square root of x graph to the left of x equals 0 in this graph. Okay, so to kind of wrap up here, differentiability fails in one of three situations. When a graph is not continuous. If a graph is not continuous, how can I even have a slope at that point of discontinuity? I can't have a tangent line that I could draw to a point that's not there. Or differentiability will fail when a graph has a sharp turn, which means the slope from the left and the slope from the right aren't the same. They exist, but they're not the same. And a graph has fails differentiability when it has a vertical tangent, because that tangent line that's vertical, that line that's vertical, has no slope. And let's just record a couple of statements on the back about the connection, the relationship between differentiability and continuity. So 2 statements we're going to write. So if a function f is differentiable, then we have an if-then statement, then that function, then f is continuous. So if we know that a function is differentiable, that implies continuity. So we'll write that down. Differentiability implies continuity. Okay, what about the reverse of that? If a function f is continuous, then f may or may not be differentiable. So just because a graph is continuous or a function is continuous doesn't mean that it's going to be differentiable. And I just want you to think of the absolute value graph. So differentiability implies continuity, but continuity does not imply differentiability.